In the last video, we saw how we could combine lenses to make microscopes and telescopes. And at the end, I mentioned that the single most important quantity in purchasing a telescope is to get as big of an objective lens as possible. We'll start to get into that, but first I'd just like to talk about how things can be not ideal in lens systems and mirror systems. The first issue, and we call these issues aberrations, is what's called spherical aberration. Oops, spherical aberration. Now, what's going on here is that the correct shape to grind for either a lens or a mirror to get all the light to come to a single focus is actually usually a parabola, sometimes a hyperbola. Now you can get away with using a spherical section as long as it's a small section, so that it looks a lot like the chunk of the parabola or the hyperbola you really need. But it's still going to be the case that your rays won't all come to the same focus. So, for instance here, if I draw my optical axis and a principal plane, and I'll go ahead and stick in a lens that's been ground with a spherical shape, what's going to happen is the light coming in at the outer edges, like so, will come to a closer focus than light that is coming in more along the optical axis. So let me just draw a couple more just to make the point clear. So close-up rays will come to a focus further out, and far-away rays will come to a focus closer in, like so. So what this means is that you won't converge to a single point. Instead, you'll get to just some minimum spot size here, and this gets called the zone of confusion. Yeah, I know, funny name. Now, as long as the zone of confusion is smaller than a pixel element in your sensor, then you're basically done, right? There's no need to get it into any sharper focus than that, because it won't show up in the image. So this is why a lot of times lenses are made with a spherical shape. It does the job good enough, and it's a heck of a lot cheaper than grinding something with the correct, typically parabolic surface that you need. But sometimes, especially for really large lenses, that just isn't going to cut it. So then the fixes is to grind it right. That will cost money. All these fixes cost money. Thankfully, with CNC machining technology, grinding it right is cheaper than it used to be by quite a bit, but it's still a lot more expensive than making a spherical surface, where you can literally grind a spherical surface just by taking a piece of glass and just rubbing it around in the form, it seeks its own center and you make a nice spherical shape. And this one will work both for mirrors and lenses. This one is only good for lenses. This is what's called a spun lens. This is where the index of refraction varies with distance from the optical axis. So using very proprietary things, the lens making companies, mostly in Germany, that have mastered this technique are not giving up their secrets too much here. Using some sort of proprietary trick, they're able to continuously vary the index of refraction of the glass going from the central axis off to the edge. By doing that, they can coax all of the rays to come to a focus in the same spot. Now, believe it or not, this is how your eye addresses spherical aberration. The eye is sort of a crystalline structure. The eye's lens is a crystalline structure, and different crystal zones within the lens have different indices of refraction. However, I should point out it isn't like a beautiful job. It just makes it less bad. It turns out that the image that you form on the back of your eye, if you were to take a photo of it, it just looks like a train wreck. The visual cortex, the optic nerve and the visual cortex do an awful lot of post-processing work to make the image that you actually see. So in the case of humans, the human eye, the answer seems to be mostly, we'll fix it in software. Another option, and this one is for mirrors, is to put a corrector plate or a corrector mirror either in front or behind it. This is what was done with the Hubble Space Telescope. It turned out that the primary mirror in the objective mirror in the Hubble Space Telescope was supposed to be ground to a parabolic shape, but due to a very unfortunate error that did not get caught due to a whole comedy of other errors, 2 digits in the CNC machining formula got transposed. And so instead of grinding a perfect parabola, there was a little bit of sphericalness added on top of that parabola. So when the Hubble Space Telescope was first launched, they couldn't bring images in to as good of a focus as they would have liked. Fortunately, a very thorough fault investigation showed up the programming error in the Hubble's objective mirror grinding. Now, there were 2 possibilities. One was there was a backup mirror that was ground correctly, that was still in a clean room. So one possibility was to fly a shuttle mission up, grab the Hubble Space Telescope, bring it back down, swap the mirror, and then fly it back up and redeploy it. So that would have involved 2 space shuttle missions, and space shuttle missions in and of themselves are insanely expensive. The solution that was settled on was to create a corrector mirror. With this particular design, it's called a prime focus Newtonian. Normally, the light from the mirror the objective mirror gets bounced off at a 45-degree angle off of a flat mirror and into the instruments that are analyzing the light. And it's just bending at a 45-degree angle just so you don't have to stick the instrument right in the way of all the light coming in. So instead of this being a flat mirror that was used to angle it in, They just made these small mirrors. There's one for each instrument. They ground them in exactly the right way to undo the spherical aberration in the objective mirror, and it worked like a champ ever since. All right, so basically that's just giving it glasses, but that can be very effective. Now, another issue, and this issue is unique to lenses, is chromatic aberration. So what's at issue here with chromatic aberration is, remember from the phenomenon of dispersion, we saw that blue bends better, right? So say if I have some, so say there's a focal point there. Actually, I'm not going to bother drawing focal points for quick reason here. So even if, say, you had a parabolic lens where everything would be coming to the same focus, if I were to look at rays of light coming in, and I'll draw them in black to represent white light here, like so. Since these are parallel, they will go through the focal point. But since it's white light, here's the issue. Blue bends better. So the blue light will come to a closer focus than the red light. And this would have to be an absolutely terrible lens, like, say, the one in the human eye, to be this bad. Yes, the human eye also has a tremendous amount of chromatic aberration that, again, is getting fixed in software by the visual cortex. There. So the issue is you can't get the light to all come to the same focus. So in fact, if you go ahead and look at this photograph here, this is an image of a light bulb that was formed by a converging lens onto a screen. And you can see I can get the filament in decent focus, but you see that blue halo around the outside? That's because the blue rays are already diverging out past the focal point, or past where the other rays are coming into focus, and so you end up getting this blue halo. Now I can go ahead and move the lens slightly, and I can get bring it closer to the blue focus, but then what happens is the red rays won't have made it to focus yet, and you end up with a red halo around the image. And there's really not a whole lot you can do about that to fix that. Now, obviously, this is very important to camera manufacturers. And so there is a reasonable fix that they have come up with. But it's not a 100% fix, but it turns out that's usually a good enough fix. The fix is to make a thing called an Acromat. Now, what an Acromat is you take a converging lens and a diverging lens, and you have to make sure that the surface of the converging lens and the surface of the diverging lens will mate up without any gaps. So you put these two lenses into direct contact with each other. And the two lenses have to be made of different recipes of glass so that they have different indices of refraction. Now, it turns out that when you form such a contraption, what you can do is you can coax any two colors of light you want to come to the same focus due to the combined effects of the two lenses. So usually the lens manufacturers will coax red and blue to come to the same focus. And then the green will still be out of focus, compared to the red and blue, but its focal point will be a lot closer. And so by doing that, instead of the spread being, say, this big, you can make the spread between the colors a lot smaller. And again, it's the same deal. As long as the blob that you make is smaller than a pixel, so then the problem is solved. And so that is exactly what camera lens manufacturers do to clean it up. And they often have to use several lenses in combination in order to fix it. The other solution, and this is the one preferred by astronomers, is just plain to use a mirror. Mirrors don't suffer from chromatic aberration at all. So that's your other choice. Finally, there's coma. And this is just irregularity. This is due to irregularities in the shape. So in the case of coma, this could amount to issues with, say, quality control in manufacturing, variations in the density of the glass in the lens, or lenses do flex a little bit, so as you point them in different directions, the lens will kind of change its shape a little bit just due to the flex. This is less of a problem with mirrors until you get to the absolutely enormous mirrors you use at major telescopic observatories, where when they change the angle, the mirror will change shape. They call that mirror sag in that case. They fix it by actually having actuators that in real time push on the mirror to push it back into the right shape. So that's called adaptive optics. And the other is just better quality control for the other issues. Of course, that costs money too. All right. So these issues will put some limitation onto how sharp of an image you can possibly get. But even if you fix all of those as perfectly as you would like, you are still limited by the resolution of the lens. So let's go and talk about what's going on there. So if you remember back to circular aperture diffraction, so we'll just recall that real quick. We had an aperture, and this is looking side on. The shape is a circle. So if I just draw it off to the side like that so we know what we're looking at, this is what it looks like to the light waves coming in. And we saw that when we formed it on a screen that we had a central maximum and then there were additional maxima coming off. And we saw that if the diameter of this hole was d, this angle here bad art. This angle here between the central max and the first min, let me draw it the other way just to make it clear that I know I've got bad art going on. Both of these angles, theta, were equal to 1.22 lambda over d. And the factor of 1.22 comes from doing a mathematical operation called a Fresnel integral. But anyway, when we go and look at this, you look at the screen, what you saw was a bright zone. Let's just say you're looking at laser light here just to make it a little clearer. You had a bright zone followed by a dark ring. That's what's out at that angle, 1.22 lambda over d. And then you had a bunch of much dimmer bright and dark zones after that. All right. So if you think about it, if you have a lens or a mirror, that is in and of itself a circular aperture. So now we got to think about what happens from a diffraction perspective if I have a lens or a mirror in the way. I'll draw a lens, but the analysis is exactly the same if it were a mirror. So again, incident wave front coming in. There's my lens. So it's going to have diameter d, just like before. And if these are indeed plane waves coming in an ideal world, they would all come to a focus at the focal length right here. So I'll just note the dot where the focal length would be. But instead, what you're going to have is a central maximum. So let me just kind of dimension that out. There we go. So this is again our angle theta, and that's again our angle theta due to the diffraction. So we end up getting a spot like that, and we'll say that spot has width W. Okay, so this width then is going to be roughly, well, this angle here is 2 theta, and this distance here is f. So if I approximate this width with the arc length, that would be 2f theta from definition of the angle. And then we can put in that the focal length is 1.22 lambda over d. So this would be 2 times f times 1.22 lambda over d. If I rearrange it, I get that the width is 2.44 lambda f over d. So f over d, hey, that's the f-stop. So you can see another characterization is that you will be less limited by circular diffraction if you have a smaller f-stop or larger diameter lens in comparison to the focal length. Of course, the bigger the f-stop, the shallower the depth of field. That's a whole nother issue. The other thing to notice too is that the wavelength shows up. So the smaller the wavelength of light, the smaller this spot will be. So for instance, blue will come to a tighter focus than red. This actually leads to some pretty crazy extremes. The Arecibo radio telescope, which unfortunately collapsed, was a very, very large reflector-based telescope, but it worked in the radio. Because radio waves are so much longer than visible light waves, even though the diameter of the dish was so big it was just literally stuck inside a valley, you could fit fewer wavelengths across it and actually had a poorer resolution than your eye operating in the visible. So you might ask, why did you even bother making one of those at all? And the answer is because there's information you can get in the radio that you can't get in the visible. So how do we define then the resolution of a optical device? Well, the sensible thing to do was a criterion proposed by Rayleigh. So let's say we'll talk about a telescope, but it doesn't really matter. So how do you know when you're looking at, whoops, that was not very well drawn at all. There we go. So how do you know when you're looking at two stars rather than one? So let's say your instrument is here. What Rayleigh proposed, and this is actually a pretty good criterion, is he said if the central max of this image is, whoops, let me bring that over, is sitting over the first minimum of the image of the other star, you can tell that you're looking at two things. If you were to look at this in the screen, what you would see is you'd actually get like a peanut shape, is what this ends up sort of looking like. So although it's still a single blob of light, it's pinched off just enough that you can tell that you're looking at two things. Oh man, I can't draw a peanut today. There we go. It's pinched off just enough that you can tell that you're looking at two things rather than one. If this angle is any bigger, then eventually this breaks apart and you clearly see two distinct things. If it's any smaller, it starts to just look like a single thing and you can't really tell that you're looking at two things. Well, how small can this angle be? Well, it's going to be determined by the location of the first minimum due to the circular circular diffraction. So the angle will be 1.22 lambda over d. So that is the how you can so this tells you how small of an angle you can look at and tell whether you're looking at two things rather than just one. So if you have a bigger telescope, D's in the bigger diameter telescope, D's in the diameter, that means I can fit more wavelengths across, and then that means that I can resolve two stars apart. Say a lot of stars are in binary systems. A lot of times we only tell we're looking at two stars because we can see two spectra overlapping each other, but the image is blurred together. The bigger the diameter of your objective mirror on your telescope, the smaller this angle can be, and then the more of these binaries where you can resolve the two stars independently. So this is also why we've built satellites that look in the ultraviolet, for instance. Looking in the ultraviolet goes with a shorter wavelength. So for the same aperture size, you can fit more wavelengths of light across, so you can get better resolution. Plus, again, there's information you can get from ultraviolet light that you can't get from visible light. But radio, you're really stuck. I mean, you're talking about wavelengths that are in the, decent sized fractions of a meter. So how do you improve the situation there? There's a trick called very long baseline interferometry, or VLBI. And so if you have two radio telescopes, if you can have two radio telescopes looking at the same object at the same time, basically on opposite sides of the Earth, like so. The images will be shifted a bit because of the difference in perspective. By having computers very carefully combine the two independent radio data signals, two independent radio signals here, what you can do is you can construct an image that has the resolution of a hypothetical radio telescope that's the width of the Earth. Now, the light gathering capability is only the light gathering capability of the two telescopes involved, but the resolution will be the resolution of some telescope that we can't even build because it would literally cover the entire Earth. So that's a trick that radio astronomers use to improve their resolution. But to show you just how fussy it is, you know, a typical observation might last a few hours, and they actually have to take into account the continental drift that was occurring on the continents where the telescopes were located during the observation. Alrighty, so that concludes our treatment of electricity and magnetism. I thank you for having stuck it through for the whole series, and I wish you the very best going forward.